Let's continue on with our calculations. So for the final F ratio, we need something called the mean squares between treatments for the numerator and the mean squares within treatments for the denominator. And this F statistic that we're going to be coming up with is a ratio between these two things. In the numerator, we're going to have the variance between treatments, which we're going to call mean squares. And in the denominator, we have the variance within treatments. We're also going to call that mean squares. The numerator is mean squares between, and the denominator is mean squares within. So what does this mean? I keep going back and forth between variance and mean squares. So mean squares is essentially just a variance calculation. But what we're doing for each is we're finding the mean squares between by taking the sums of squares between divided by the degrees of freedom between. That is a variance calculation that we're calling the mean squares between. We're going to do the same for the sums of squares within and the degrees of freedom within. This is essentially a variance calculation, but we're calling it mean squares within. So we are looking at the variance as a ratio. So what we've done so far is we filled in our sums of squares and our degrees of freedom, and now we can figure out those mean squares. Like I just said, it's a variance calculation. So for the mean squares between, we're just taking the sums of squares of 20, dividing it by 2. And the mean squares within, we're taking the sums of squares of 66 and dividing it by 27. And that gives us the mean squares between of 10 and the mean squares within of 2.44. So the final calculation is just to take that mean squares between and divide it by mean squares within, and your data table has that all set up for you to be able to do. So before we do that, when there's really small error within in the denominator and a large treatment effect, the mean squares between, that will give us a large F score. Think about it. If you have a large numerator and a small denominator, the resulting calculation is a large F score. If our F score is large, we're more likely to reject the null hypothesis. So on the other hand, if the F score, if the two ratios are balanced, the mean squares within is about the same as the mean squares between, that gives us an F score that is equal to 1. And the numerator and denominator in this case are measuring the same thing. What this is saying is that there's no treatment effect, that both of the variance in the numerator and the denominator are just random error. So a larger F score would mean that there's a significant treatment effect. So keep that in mind, a larger F score. All of your F scores are going to be positive because they are ratios where the numerator is always going to be equal to or larger than the denominator. So that would indicate a significant difference among the means. So we want to determine whether our F is statistically significant. We use an alpha level, just like we've done before. We also use degrees of freedom like we've done before, but this time we're going to use two sets of degrees, or two different degrees of freedom between and within. So we have the degrees of freedom for the numerator, the between, and degrees of freedom for the denominator, the within. So let's see what this looks like in this study. So as you'll notice on the F table, we have across the top the degrees of freedom for the numerator. Those are the degrees of freedom between. And on the side, we have the degrees of freedom for the denominator. Our study, if you'll recall, we had 2 degrees of freedom between, and 27 degrees of freedom within. And if you draw a line together, that gives us a critical value at 0.05 of 3.35, which means that our F statistic needs to be more than 3.35 in order to be significant at the 0.05 level. You'll notice that there's some bold numbers in the second row for each of the degrees of freedom on the left-hand side, and that's just because that gives you the significance level at 0.01. But we normally do 0.05, so we're going to be just looking at the ones that are not in bold. So our significant level, our critical value in this case is 3.35. So how do we get our F statistic? We simply take our mean squares between and divide it by the mean squares within. 2.44 goes into 10 4.10 times. And this is how we would write it out. The F statistic with 2 and 27 degrees of freedom, right here and here, is equal to 4.10. So our critical value, let's go back, was 3.35. So what do we do in the case of 4.10? We reject the null hypothesis that there is no difference between these means. We say there is a difference between the means. So if there's no statistically significant result, again, the ratio is balanced, close to 1, and the distribution is positively skewed. The shape of the distribution is going to depend on the degrees of freedom. As you get more degrees of freedom, you will have a different shape of the distribution. F values are always positive, as I've mentioned before. So, ready to put this all together? We're going to give this another try in a full hypothesis test. I'll see you at the next video.